Well, welcome everyone. It's my great pleasure to introduce Adi Nusser, who's here. He's actually here on sabbatical, about a little split between here and MIT. So stop by and say hello to him. So Adi got his PhD from Hebrew University. He was a postdoc at UC Berkeley, at Cambridge, not this one, but the one in the UK also, at Institute for Astrophysics, and then also in Germany at the MPIA, so he's been all over the place. Generally, sorry I have my notes here, I was very, about 30 minutes ago I was told I was introducing him, so normally I remember this stuff.
The reason is that Shmuel Bialy's wife is about to give birth.
That's right, so, well, yeah, so that we're all very excited about that, but let's not let that distract us from this exciting talk.
Let's see if it's more exciting.
The probes. So today he's going to tell us about the probes of structure formation in the universe from dark matter and alternative gravity.
Thank you very much. So I planned my talk for 40 minutes. I'm not sure if that's going to happen, but you know, that's the plan. So I will start with the standard stuff, talk about the standard lambda CDM, but I will not talk about the standard probes which you hear about all the time, but something else, a little bit different. I will talk about the importance of beating down the systematics, and that's why I would like to introduce a new probe large-scale structure. Perhaps it's actually an ancient probe, not that new, you will see. Talk about non-standard cosmological models. Despite the success, I will argue that we may need to think outside the box a little bit. So let me see, so this is the success of the CDM on large scales. Everybody knows that. It's very impressive that you start from very tiny initial fluctuations, you get to the structure which we see, and there is a lot of information in the data at high redshift, low redshift. This is standard stuff. People here have done fundamental work on this. I would like to introduce the equations, and this is important for things to become later. The data will show later. Let me see. Let me try this. Okay, so this will work nicely. So this is the standard equations. Now, just you have the Euler equation. Doesn't work. 12 before. Now, in modified gravity, in non-standard cosmology, you can do two things. One thing is that you can change this side, and this is in theories like, I don't want to just throw names, I will give an example later. Einstein ether theories, things like that, things which break the Lorentz invariance. You can have actually additional terms here, things which also break the equivalence principle. All modified gravity theory sort of fallen into this kind of modifications. We have gas, which I will not include in the equations for gas I'm not including here. We will notice here that these are Newtonian equations. What about GR? So it's remarkable. The GR version of these equations is very, very similar. Think about the Friedman-Robertson background. The same Newtonian equations would give the same GR equations. If you look at nonlinear evolution of perturbations, the same evolution you would get in both theories, in the Newtonian version and the GR version. It's remarkable.
You're ignoring the pressure also.
I am ignoring the pressure, but of course you can put that in.
And we know also the dark matter.
Sorry?
The dark matter could potentially.
Yes. But this is, minor modifications compared to modifications I want to talk about. This is okay. So just to make some sense out of this, one of the most important relations that we get out of this is this thing. It's very intuitive. The velocity is proportional to the acceleration times the cosmic time. It's just the Hubble time here. It's really intuitive. The exact relation is what's interesting. It involves cosmology. Omega, lambda, everything else, and this is if you have a dark matter model, dark energy model, which with an equation of state which goes like rho P equals rho to the power W, which is responsible for the acceleration, you get a very important quantity which is called f of omega, and this fixes the growth rate of perturbations. This is something which you can measure from data, and this is a very important quantity to measure. Okay, just to give you an idea about this growth rate, so this is in the lambda CDM model. This is not data, just some sort of prediction of theory. And f of r models where you change gr instead of the term the linear r, you change it to some function f of r. This is here also. This is the type of differences that we're after. Okay, so the probe, which is very controversial, and this is, I think, because it has been misused by the community. Some people did it well, some people didn't do it well, is motions of galaxies as a probe of the dark matter. Okay? And the first impact of these peculiar motions, which are deviations from the Hubble flow, you would see it in the distribution of galaxies when you observe it in redshift space. It's very easy to observe redshifts, measure redshift galaxies. Distances are much harder. Okay, like all these catalogs which people are talking about, you measure redshifts and you can plot this is just a toy model, and you can plot the galaxies as a function of the redshift. So this is, if this is in real space, look what will happen if you measure it in redshift space. This is an exaggerated view. Work, please. Oh. Strange, didn't want to work. Okay, let me see now. Okay, I'll try it this way, because it's really nice. Okay. So this is redshift space. Redshift space, back to real space. This is exaggerated, of course. And you would notice that in redshift space, things are not isotropic, and this lack of isotropy, so this is here in real space, the real distribution is isotropic, but the actual universe, when you observe it, this is the galaxies at the redshift position, they would look non-isotropic. So, you know, if you look at this picture and you want to say, oh, is the universe isotropic, you'd say, oh, no way. But actually, this is an artifact that we're plotting things in redshift space. So, okay, so redshift space are a great, really very important probe of the structure and of the growth rate and whatever you want in cosmology. However, the challenge now with future catalogs, they're very large, they give us very precise information, but the challenge is systematics. We have to beat down systematics. A very good example of that is the Hubble Constant, or I hear that people call it Lemaitre, Hubble Lemaitre these days, even though Lemaitre never actually plotted it. So there is a very old disagreement between Vauquelin and Sandage, and now we have a disagreement between the local measurements of the Hubble Constant and the Planck result. So it's not small, it's a 4 sigma. It's a small difference, but it's actually significant. So I thought, oh, I saw this paper, and I thought, that's it, it's resolved. There has been a paper by Friedman and her group, and they recalibrated the supernova based on a different calibrator, the TRG, divergent branch distances, and they got something very close to the Planck result. I said, oh, that's fantastic. Done. But then again, no. The other group, the group of Rees, did not remain quiet. I said, no, these guys have a problem with the calibration. So we're back to square one, or even 0. Okay, so why am I talking about peculiar velocities? The good thing is that you can make the analysis completely independent of H0 just by taking out a monopole term in the motion of galaxies. The second thing, they are really the only probe of the 3-dimensional dark matter distribution. Lensing is 2D. Peculiar velocities are 3D. The bad things are usually a small number of galaxies, sparse data, mostly nearby, and they're very hard to analyze. So this is one of the most important relations with which we measure the velocities. It's the luminosity versus the rotation of galaxies, that's in the spiral galaxies. And this intrinsic relation, this quantity doesn't depend on distance, this depends on distance when you measure the apparent magnitude, and you can calibrate that to get the distances of the galaxies. So what's all this thing here? So these are the measurements. Actually, I'm cheating even. These are individual velocities in the supergalactic plane, not even the measured velocities, as they are smoothed a little bit. Okay, so here is one thing. If you take the average velocity here, radial velocity of these galaxies, we can measure only the radial component of the curve velocity. Then you get something like 700 kilometers per second on a large scale. That's way, way, way beyond what you expect in a lambda CDM. So you go run and publish a paper, you rule out lambda CDM. And this has been done, not on this particular case, but in other cases. Okay? So managing the error is very important, and understanding the data is very important in this case. Okay, I just made the point which I'm trying to make here. Okay, but we have something very nice about our universe, is that locally it's extremely quiet. So we live in the Milky Way. The Milky Way belongs to the local group, and there are galaxies around. And we don't live in a cluster. All galaxies share this almost the same velocity field, peculiar velocity field. That's a great advantage because it gives us the tools to analyze the data without having to worry about local nonlinearities. Okay, that's just pure sheer, I don't know if it's why that is. It's very hard to understand why we're so lucky. For example,